In this video, I'm going to show you the proof rules for the remaining logical connectives, both the traditional way of writing them on paper and also how they look in USC. Last week, I told you about implies and the ones we have left are or, the constants true and false, and not. Or has two introduction rules. To prove P or Q, it's enough to prove P. And also to prove P or Q, it's enough to prove Q. So these are called or introduction left and or introduction right. For the elimination rule for or, we have to think, what can we do if we know that P or Q? This is the most complicated rule that we've seen yet. So if we know P or Q, and we know that if we have P, then we can get R, and we also know that if we have Q, then we can get R, then overall we can get R, since one of those two things will always happen. So the proof rule looks like if we know P or Q, and given P, we can get R, and given Q, we can get R, then overall we have R. This is or elimination. So you can think of this a little bit like a switch. Either the middle branch or the right branch will work depending on what the left branch says. The next set of rules we have is for true. So true is a bit like a propositional variable, but it's actually a constant, namely it's the formula that's always true no matter what. The introduction rule for true is very simple. We can always get a proof of true for free without having to supply anything else. So we always have a proof of true with no hypotheses, with no previous proofs above the line. So this is true introduction. And there is no elimination rule for true because the knowledge that true doesn't actually tell us anything that we didn't already know. So here there is nothing. Next we have false, which is similarly the propositional constant that's always false. There is no introduction rule for false because we can't actually get a proof for something that's false. But the elimination rule for false is very powerful. If we have a proof of false, then we can get a proof of anything. So if we have a proof of false, then we can get a proof of P. This is false elimination. So in logic, this is sometimes called the principle of explosion, which says if you have a contradiction, then anything can happen. So you might think that this sounds like a huge waste of time. What's the point of having this very powerful false elimination rule if we can never actually use it because we can never actually get a proof of false? Well, it turns out that this is useful when you combine it with the next set of rules, which are for not. I need a new page, which I can do like this. So for the introduction rule for not, we have to ask, how do we prove not P? Well, if assuming P allows us to derive a contradiction, then it must be the case that not P. So the rule says, if I have a proof of false from the hypothesis P, then I can get a proof of not P from no hypotheses. Now, this is called not introduction. Now for the elimination rule for not, what can I do with the knowledge that not P? Well, if I know that not P and I also have a proof of P, then that's a contradiction. So I can put them together to get a proof of false. So if I know not P and I know P, then I know false. This is not elimination. Okay, now let's switch over to ask. I share screen here. Now I'm going to start by introducing a brand new feature that we didn't have a So sometimes ask decides that one of your sub-goals is so completely trivial and boring that it doesn't even bother to show it to you. So the instance of this that you've already seen is when your goal is the same as one of your givens. There are two other trivial cases which cause the same behavior in ask. One is when the thing that you're trying to prove is the constant true, and the other is that when false is one of your givens. So the new feature we have is that in each of these three cases, there is now a proof rule which you can write to make it explicit. So to show you an example of this, if I send prove P implies P by imp I, then ask sends it back unchanged. Prove P implies P by imp I, then ask sends it back unchanged. But I can also write where, and on the second line, I can write given P, prove P, given. So the keyword given is being reused here as a proof rule. So both versions of this proof are equally valid, and behind the scenes in the back end of ask, these are secretly the same proof, but they're being displayed in two different ways. Okay, now onto the new proof rules. If I send prove A or B by or I L, then ask tells me that I need to prove A. Similarly, if I send prove A or B by or I R, then ask tells me that I need to prove B. Okay. Now, if I set myself up a situation where I have A or B as a given, like this, then I can say from A or B, and ask will generate two sub-goals, one where I have to prove C from the hypothesis A, and one where I have to prove C from the hypothesis B. Okay, the introduction rule for true is one of the things that ask does automatically. So if I write prove A implies true by imp I, then ask sends it back unchanged. But I can also write where given A prove true by true I. That's the name of the introduction rule for true if you want to make it explicit. And as I said, there is no elimination rule for true. That includes in ask as well as on paper. And also remember, there's no elimination rule for false. So next we, there's no introduction rule for false. So next we go on to the elimination rule for false. That's also automatic. So if I say prove false implies A by imp I, then ask sends it back unchanged. But I can also write where given false, prove A from false. And that's how I make the elimination rule for false explicit. Okay, so the thing that we have left is the rules for not. The introduction rule for not is called not I. So I can write prove not A by not I. And ask will say that I need to prove false given A. Okay, so for the elimination rule for false, let me set myself up a situation where I have a not A given. This. Now I can say from not A, and then something maybe a bit surprising happens. Ask tells me that I have to produce a proof of A. So when I wrote this on paper, I would have had to, this elimination rule would give me a proof of false. What's happening is that ask is still doing false elimination automatically. So it knows that if you can get false, then you can also get B, which is the thing that you're actually trying to prove here. Okay, and that is all of the rules, except no, I'm afraid that's not all the rules. There is one more rule left which doesn't fit the pattern, and that rule is the subject of the next video.